Now we come to the third part of the class, which is how to represent floating point numbers. We will discuss about this briefly. Now, so far we have discussed how to represent integer numbers as well as signed integer numbers. But how do we represent the fractional part of the numbers? Now, you could think of various alternatives. For example, you have to remember that in the computer, there are only 2 bits, 0 and 1. We do not have another bit, which is another symbol, which is the point. So the entire number has to be represented in terms of ones and zeros. If we want to use the decimal point notation, since we cannot use the point itself, we can assume a position for the point. So we can assume a decimal point before a 2's complement number. If we assume that, we can represent pure fractions but not mixed numbers. We can also assume that the decimal point is in position 7 or 5, right? But this will lack flexibility and we will not be able to represent very large numbers or very small numbers. So if you have 16 bits for the number, if you say after 8, we can assume that the first 8 bits are the whole part and the last 8 bits are the fractional part. So it restricts the magnitude of the number that we can represent. So we adopt something called the mantissa exponent method and to represent floating point numbers. And we will conceptually discuss this representation, but we will not talk about the particular representation which is. So a floating point number f, we can represent it by a doublet m and e, where m is called the mantissa and b is called e is the exponent and b is the base of the exponent. We can think of f equal to m into b to the power e. And we typically, for binary numbers, we take b equal to 2. So a number we can represent as, let us say, 0.101011 into 2 to the power 0110. So we can, for example, in a decimal number, we can represent, let us say, 6.02t into 10 to the power 48. So this is a way to represent floating point numbers. And this is done in terms of the mantissa and the exponent. Now for the mantissa, because we are also interested in representing fractional parts, we can make an assumption that the binary point is to the absolute left. Right? And therefore, we can write this number as 0.6023 into 10 to the power 49. Now, once we adopt this convention, we can use this to be the mantissa and this 49 to be the exponent, and this base typically in the binary system we will use as 2. So this number m, we assume that there is an implied decimal point before it, and m can be both positive or negative, and therefore we represent m in 2's complement form with the assumption that there's a decimal point before it. And the exponent is also represented in 2's complement form. So out of the number of bits available for representing the floating point number, we use certain number of bits for storing the mantissa and certain number of bits for storing the exponent. These are examples of this notation: decimal 0.235 into 10 to the power 6. The mantissa is 0.235, exponent is 6. In binary, this is an example that the mantissa is 0.101011 and the exponent is 0110 and the base here is 2. So suppose you have a 32-bit floating point number. This is just a thought exercise. Suppose you use 24 bits for the mantissa and 8 bits for the exponent. And for m, we assume that there is a decimal point to the left of it. Therefore, the largest m is bounded by 1 and the smallest m is bounded by -1. So m is between +1 and -1. Okay. So m can actually represent 0.24 ones, which is close to 1. And E is also represented in 2's complement form. And since we have 8 bits, E will represent numbers from +127 to -128. Now, the points to note about this representation is that the number of significant digits depends on the size of the mantissa, number of bits in the mantissa. If the mantissa had, if you had this 32 bits, you could have used 8 bits for the mantissa and 24 bits for the exponent. If you use 8 bits, you can represent only a certain amount of precision. So the number of significant digits which impacts the actual precision. For example, suppose you want to represent the value of pi, right? If you restrict to 2 digits or 3 digits, you have a lower precision value of pi. If you allow more number of digits or bits, you can get a higher precision. So the size of m is the number of significant digits, which tells you to what precision, what resolution you can represent the value of this floating point number. On the other hand, the exponent, because you are talking about 2 to the power this exponent value or 10 to the power this exponent value, if this exponent is large, you can store larger numbers as well as smaller fractions. Right? So the range of numbers depends on the number of bits in E. So if you have an 8-bit exponent, it can store from 2 to the power 127 up to 2. So up to 127 and down to -128 to the -128, which is equivalent to approximately 10 to the power 38, and the smallest fraction is 10 to the power -38. So if you are given a number of bits, you can break up. You can assume that part of it is for the mantissa and part of it is for the exponent, and there's a trade-off. Larger the mantissa, more the precision, more the number of bits, and larger the exponent, more the range of the numbers that you can represent. We are not looking at the actual representations, which is a little bit more involved, like IEEE floating point format, but this gives you a basic idea about how a floating point number is stored in the computer. The actual representation is a little more complex, so we'll not cover it here. So in C, floating point is typically a 32-bit representation. Double is high precision floating point, which is 64-bit representation. Okay. So this is in very brief how a floating point number is stored. Now we have discussed how to store binary numbers, signed numbers, floating point numbers. Next, we'll very briefly talk about how characters and strings are represented. In computers, have to store all type of data items. We have already discussed this, but let us look at how a character is. So we will look at what are the characters which are available in C. Now, there are certain sets of characters which are used. There are various standards. There are 3 standards which are commonly used. One is slightly older standard called EBCDIC, which was used in older IBM machines, not so popular now. The very popular code that we often use and we use in C is the ASCII code. It's very widely used. ASCII stands for American Standard Code for Information Interchange. And ASCII uses 8 bits and represents 128 different characters. However, people also use Unicode, which contains various international characters. So if you want to use Devanagari characters or Japanese characters or other multilingual characters, one uses Unicode. Java typically uses Unicode. In C, we normally use ASCII. Now, as I told, in ASCII code, every individual character is numerically encoded into a unique 7-bit binary code. And therefore, there are total of 128 different ASCII characters in standard ASCII. There is also the extended ASCII characters, which is another 128, but that's not what is there in C. So if you have 8 bits to represent a character, the MSB is not used. The rest of the 7 bits are used to represent the ASCII code. And the binary encoding follows a regular ordering. For example, if you look at the code, this ASCII code, this 128 characters includes the 10 digits 0 to 9. It includes the lowercase letters small a to small z, the uppercase letters capital A to capital Z, as well as other symbols like plus, minus, bracket, question mark, full stop, backslash n, backslash 0, and so on. And the exact codes are not easy to always remember. However, you must remember that capital A, in the code of capital A, code of capital B, they are closely related. These codes are one after the other. So capital A has a code of 41 in hex, capital B has a code of 42 in hex, C as 43, D as 44, and so on. And up to capital Z is 5A. Similarly, small a has 61, small b 62, small c 63. So the code for small f is one more than the code of small e. And the codes of the capital letters are smaller than the codes of the lowercase letters. Then we have the codes of 0, 1 to 9. They are also consecutive. And then we have other characters. The next thing that we have already discussed is how character strings are stored. As we have discussed in C, when you have a character string, we store the individual characters and then we terminate. We use for the next cell, we use the null character, which is backslash 0, whose ASCII code is 0. So this backslash 0 is used as a string delimiter, which we have already discussed. With this, I will finish today's lecture. And if you have any questions, please let me know. Thank you very much.